Welcome back to Physics 152 Online. As we've studied Faraday's law and the phenomenon of electromagnetic induction, you might have wondered, well, what difference does this make in electrical circuits? Or how can we apply this in a practical way in electrical circuits? So we're going to talk today about the influence that this phenomenon of electromagnetic induction has on the behavior of currents in simple circuits. So the point that's really important to realize is that any time an electric current flows in a circuit where there's a closed circuit loop, the magnetic field it produces will create a magnetic flux through the circuit loop. So here's a simple schematic diagram where we see a power supply and a resistor in series with a switch. So when the switch gets closed, the current that begins to flow using the right-hand rule, you can see that that current will produce a magnetic field that in the interior of that conducting loop points into the page. So the current in that direction clockwise around the circuit, consistent with the polarity of the voltage source, will give us a magnetic field that's pointing into the page inside the circuit. And here's the important point. As the current increases from its initial value of 0 to whatever its final value is that would be given by Ohm's law, there's a changing magnetic flux through that circuit loop. Therefore, Faraday's law says that there will be an induced EMF that will oppose the change in flux. So think about this. If the magnetic field is pointing into the page and it's increasing, then there will be an induced B pointing out of the page that opposes the change in flux. And that means there will be an induced current in this loop in the counterclockwise direction that opposes the current that's changing from 0 to its final value. So we call this kind of an EMF in a circuit a back EMF because it opposes the change in the original current that was in the circuit. So practically, what this means is in any circuit, no matter how simple like this, there will always be an opposition to the change in the original current flow. If we close the switch at time t equals 0, the current will begin to build up, but it won't reach its final value instantaneously because of the back EMF that generates an opposing current. So it'll take a certain amount of time for that current to approach its steady state value. And we call this effect self-inductance because the phenomenon of induction that is present in this loop was caused by the very flow of current in the loop to start with. So any circuit, no matter how simple, will have at least some small amount of this self-inductance phenomenon. But we can magnify the effect significantly by using a coil of wire or a solenoid with a large number of turns. And if we put that into the circuit, and we call that circuit element an inductor, it's going to magnify the amount of the back EMF that's produced. The symbol L is used to quantify the amount of self-inductance that that inductor has, and it's going to depend, just like when a capacitor, when we talked about capacitors, the capacitance value depended on the size and shape of the conductors. Here, the self-inductance of that loop, of that coil, is going to depend on the size and the shape of the coils. So you can see why this effect will get magnified, because not only then will we have a flux that's through the original circuit loop, but because now a current will be passing through each of the windings of this coil, you'll have a large flux change because of the changing current through the inductor. So the more turns that you add, the larger the effect will be. So the field inside the inductor won't be a uniform field, not generally speaking anyway. For a solenoid it might be close to being uniform, but even at the ends of the solenoid the magnetic field strength changes. But what we can say for sure is that the field strength is proportional to the current, right? and the flux through the coils therefore will be proportional to the current. It won't necessarily be easy to calculate what that is except for certain very specific shapes, but what we can do is introduce the idea that the magnetic flux through those coils, which we know is integral B dot dA, integrated over the surface that those coils define, that flux is proportional to the current that flows through. And L then becomes the proportionality constant between the current flow and the net flux. And of course this net flux includes the number of turns of wire that there are on the coil. So that's the definition of self-inductance. It's if we were to solve for L here, it's the magnetic flux divided by the current. And L will depend, as we said, on the size and the shape of the coil itself. The units of L, if we were to solve for L here, we could find out what its fundamental units would be, but we define the units for self-inductance as the Henry in honor of Joseph Henry, who was a great American scientist in the 19th century and was a contemporary of Michael Faraday's. So the back EMF, this induced EMF that happens in the circuit because of the presence of the inductor, we can figure out what that is by just going back to Faraday's law. All right, so E, the EMF, is minus the time rate of change of flux, and now with our expression for flux defined as L times I, we just take the derivative of that. L is a constant, so it's just minus L di dt. And we see that this induced EMF caused by an inductor, by current flowing through, changing as it flows through an inductor, is equal to minus L times the rate of change of the current. Now, one last thing that we can easily quantify, and if you think about the operation of an inductor, if what I've said is true, the back EMF that happens when the current flowing through the inductor changes, that always tries to maintain the original current flow. It opposes the change, and by opposing the change, it's acting to try to keep the current flowing at its original rate. And that requires energy. So where does the energy come from? The energy is stored in the inductor, and we're going to now quantify what that is. So all we have to do is use our expression for this back EMF that the inductor produces, and remember that the definition of power is I times the voltage, in this case provided by this back EMF. So the power that is supplied by the inductor is equal to I times E. E is minus L di dt, so when we put that in here, you see what I've done is I've dropped the minus sign because we don't really care about that. We just want the magnitude of this power. And power, by its very definition, is the time rate of change of energy. So if we use U to symbolize the energy that's being stored in the inductor, we can solve for du and find that it's equal to L times I times di. And it's kind of a strange looking expression, but what it tells us is that when the current changes by a tiny amount di, the energy that is required, or the energy that is stored in the process of that changing current, is equal to the inductance times the current value at that point times the change in the current. And in order for us to figure out what the energy storage is in total, we can integrate both sides of this equation. So we, on the right hand side, will be integrating from the initial current of 0 before the switch is closed to the final current that flows through the inductor when it reaches its steady state value. I put primes on the di and the I here. And then the left hand side, that means we're just adding up the sum of all of the energy that gets stored in the process of this current beginning to flow through the inductor. So it's an easy integral to do. You see we get I squared over 2, and when the smoke clears and we solve for the total energy storage, we get 1/2 times the self-inductance times the current squared. You'll notice, if you remember the formula for energy stored in the electric field of a capacitor, that this formula looks pretty similar, except that the important parameter for the energy storage in an inductor is the current, the square of the current, while for a capacitor it was the square of the voltage that was applied to the capacitor. So the proportionality constant for an inductor is the self-inductance, for a capacitor it's the capacitance, but there's a striking similarity between those two equations. And just as we were able to show that the electric field in the capacitor is what stores the energy. It's the fact that there's an electric field now inside the capacitor plates, and the energy is stored in the presence of that electric field. The same kind of thing holds true for an inductor. The energy that's stored in an inductor is stored in the magnetic field of the inductor. And so we'll be able to, in class I'll show how you can re-express this formula for the energy storage in terms of the magnetic field strength inside the inductor. We did something similar with capacitors, where we showed that you could express the energy storage in a capacitor in terms of the strength of the electric field itself. So hopefully that introduction helps you a little bit to understand what we mean by inductance and its influence in electrical circuits. An inductor's presence in an electrical circuit always acts to oppose the change in the flow of current. I'll see you in class.